So if we go all the way back to the guesses that we made about line integrals and double integrals, there are two things that we guessed, but so far we've only talked about one of them. We guessed that the circulation around the boundary is equal to the total circulation over the interior, and that was this equation, and this we proved, right? That's what we called Green's theorem, but we also guessed that the flux through the boundary should be equal to the total flux over the interior, and we haven't thought about this problem yet. So let's think about flux. Our goal is to prove that the flux integral out across the boundary, and remember this means outwards across the boundary, should be equal to, we think it should be equal to the double integral of the divergence of the vector field. You might think, oh no, this is going to be a big awful proof like proving Green's theorem to begin with, but actually there's a pretty slick trick that will make this much more straightforward, and that is, so we have this vector field f. Let's invent a new vector field called g. And g is going to be minus n comma m, where n and m are these coordinate functions for f. So let's do the integral of f dot n ds. So this is, remember, this is the integral of f dot, sorry, I need to write out what f is. F is m comma n dot y prime comma minus x prime dt. Okay. Well, this is the, and then the bounds, I won't write the bounds every time, but whatever the bounds need to be. Okay, so this is the integral of m times y prime minus n times x prime dt, but we can write this as a dot product in a different way. We could write this as, right, to make this a regular line integral, we'd rather have r prime right here, but we can make that happen. If we want x prime and y prime to be here, to get this same thing for the dot product, our minus n has to be multiplying x prime, so it belongs over here, comma, and then m has to be multiplying y prime, so m belongs there. Okay, so these two things are equal, just because if you work out this dot product, you do get that stuff in that integral. Okay, but notice that this is g. Right, so now we have the integral over our boundary curve of g dot dr, right? Because this is dr, or r right here, or r prime, and I forgot my dt. Okay, but Green's theorem, right now we have a regular old circulation integral. It's for a different vector field, but still, this is a regular old circulation line integral, so we can use Green's theorem. And Green's theorem says this is the double integral over the interior of the region of the curl of g. But remember, g is minus n comma m. Right, this is g. dA. So what is the curl of this vector field? So the curl of this vector field is partial r, not partial r, not the boundary, r itself. So the curl of this vector field is, right, it's the partial derivative, partial with respect to y, partial with respect to x, of the y coordinate function, which is m, minus the partial derivative with respect to y of the x coordinate function, which is minus n dA. Okay, so simplifying things just a little bit, this is the double integral over r of partial m partial x minus minus, so plus partial n partial y dA. But this is exactly the double integral over r of the divergence of the original vector field f. Okay, so we started with the integral over the boundary of r of f dot n ds. And what we got was the double integral of the divergence. So this thing that we guessed for vector fields about divergence and the flux integral is true for all of the regions for which Green's theorem is true. All right, so just a quick example about this. Let's find the flux of this vector field outwards through this circle of radius 2. If we computed this using a line integral, again, we get a big messy pile of trig stuff. If we switch to a double integral, right? This circle is radius 2. So instead of finding a flux, we could do a double integral of divergence of this vector field. So to see if this would be easier, let's calculate the divergence of this vector field. So partial m partial x is going to be minus 2xy plus partial n partial y, well, that's 0, dA. So this looks like it would be much easier to do than the big messy line integral that's going to involve a bunch of trig stuff. So let's calculate this double integral. It's going to be easiest to use polar coordinates because the region is a disk. So this is going to go theta values from 0 to 2 pi, r values from 0 to 1, so that we're from 0 to 2, so that we're going from the origin out to the edge of the disk. And our integrand is minus 2 times x, which is r cosine theta in polar coordinates, times y, which is r sine theta, times dA, which is r d theta, and now it's a double integral that we can compute. So I'll work it out. Fortunately, we can separate these integrals. The constant we can move all the way to the front, minus 2. The theta integral is the integral from 0 to 2 pi of cosine theta times sine theta d theta, and then times the r integral from 0 to 2, looks like we have r cubed here, d theta. So minus 2 times this integral. You can either use trig identity, so it turns out this is equal to 1/2 sine of 2 theta, or you could do a little u substitution because the derivative of sine theta is cosine theta. Let's, just for variety, let's do the u substitution. So the u substitution is going to turn this into the integral of sine I'm letting u be sine theta, so du is cosine theta d theta, and our bounds are going to be from 0 to, right, when theta is 0, sine is 0, and when theta is 2 pi, sine is also 0. So this integral, right, we actually don't need to work out anything else because this integral is going to be 0. So we get 0. Which, yeah, that makes sense. That makes sense because if we had used the trig identity way, this integral would have turned out to be 0 as well. So I believe it. We get 0. So this integral was much easier than the big messy integral with, right, large powers of sine and cosine. So using the flux version of Green's theorem saved us a lot of work here.